Have you hand those up and over now with the dash 3. You guys are 3, right? Dash 3 after it. Let's have you, and make sure you put that on all the stuff you hand in. And hand those up and over now. You all should have 2 things out on your desk. Let's bang out one of them pretty quickly. Make sure your note packets are out as well. We're going to do the function of the week stuff, and then we'll get to your homework. And those up and over, and go. Make sure your note packets are out and your homework, and you've signed into your calculators. So far we have, oh good, almost no one signed into the calculator. Just what I was hoping for. So if you haven't already, please go through and sign in. We left off, and we'll talk about this first. Yesterday we started off with square root, so our function of the week is going to be y is equal to the square root of x. We'll get to the homework after. Looking at what we have, let's start talking about what this graph is going to look like. So instead of mindlessly going into the calculator, who can tell me an input that's going to give us an output if that's our function? Hands up, please, if you can tell me an input that's going to give us an output if our function is y equals the square root of x. 0, if that's my input, what's the output? Okay, that's 1 point that's going to be on the graph. Who can give me another one, please? What do you want to say? Okay, we got 25.5. Unfortunately, that's not going to fit on our graph, but it's going to help us establish behavior. Go ahead. Nine is going to give you out a 3, and that does fit on our graph. Who can give me another point that would be on this relationship? 16 and 4, is that going to fit on our graph? No, again, but it shows behavior. What's another one we can go through and list? 4 and 2 is going to be on the graph, so let's list that out, please. There's one more we should be able to list out, kind of easy. 3 people, yeah. 1, 1 is going to be on there. Notice if you only grab 0, 0 and 1, 1, it looks like the identity function from before. Now I can continue this out. We would get 36, that's 6, 49, 64, 81. When I plug in a 36, I get a 6, 49 gives you a 7, 84 gives you, or 8, 64 gives you an 8, 90, 81 gives you a 9. Notice what's happening and where the data is going. What's the domain of this? Take a look at your graph. What would our domain on this end up being? Jared, what do you think? Okay. Terrific. 0 out to positive infinity. What about the range on this? Those are the y values that we use. What do you want to say? There you go, 0 to infinity. The domain and range are the same. Next one up, when is this increasing? Remember, it's only as you move left to right. Who can tell me when this is increasing, from where to where? And again, you've got a whole crop of values to be looking at. From where to where does this increase? One person? As I move left to right, when am I stepping higher than I was before? At 1, the function's increasing. What interval is it increasing over? No. You're not wrong, but you're not all the way there. Close. It's going to be from 0 to positive infinity. Our notation and the state regent's notation is not to include where that begins, because it's defined as you proceed from left to right is the point that you're at higher than the one before. And if I start off at 0, there's no point behind me, which is why the 0 gets a parentheses and not a bracket. Everything after the 0 works, but the 0 itself has nothing behind it. When would this be decreasing? Take a look at this. As I move left to right, keep in mind you can only move left to right. When would this be decreasing? It doesn't. If it's always increasing over its domain, it's never decreasing. When is the function going to be constant? What do you say? It isn't. You could also give the empty set, null set. Next one up, when is the f of x or function values, when are those going to be greater than 0? Looking at that, Eli, what do you say? When is the function values or y values greater than 0? For what axis? Close. When is it greater? He said 1 and up, and he even did the right integers. But we want to add one little bit to it. Anything bigger than 0. So 1 and up works, but it's not everything. We need to put parentheses there. 0 out to positive infinity is when it's greater than 0. When is this less than 0? For what y values is this going to be less than 0? I think it like put the 2 a little bit. 3 of us? 4? You never use those y values that are negative. What about when does the function equal 0? At 0. So we could give it out as a bracket and just make it a closed single integer interval from 0. And you could also, I guess, if you want, list it out as a set of values and plug only a 0 into it. Either one of those is fine. The zeros of the function themselves, when you go through to find the zeros, you need to show it algebraically. You would set the y equal to 0 and then solve. So if I did this instead of y equals root x, I'd say 0 equals root x. What do we do to solve that equation out, Cassie? So what would you have if you squared both sides? Or if you were to list it out as an ordered pair, because technically the zeros are referencing where it crosses the x-axis. So we know what happens when x is 0, or what other ordered pair does it happen at. 0, 0, which is the origin. Either one of those is okay. Looking at the graph, what would we say are its maximum or maximums? Luke, what do you think? It goes out to positive infinity. Is that a number? No. So it's not going to have a maximum. You could put DNE for does not exist. It will have a minimum. He's right. It keeps rising to positive infinity. It's unbounded above. What about our minimum value? 3 of you. Oh.
0.
There you go. So we'll state it as, and this again is something that your language matters when we list this out. It's asking for the minimum. Now, if it's asking for the minimum value, that's the x that the lowest point occurs at. If it's asking for the minimum value, that's the y. If it says where is the minimum, you would go through and say at x is equal to 0. In this case, it doesn't, so we'll specify the ordered pair. It goes where, comma, value in terms of x, comma, y. Next one up, we need to state what the inverse is going to be in any domain restriction. This is one that some of you struggled on before. What do we need to do first off to find out what our inverse is going to be? Alexa, what do you say? Terrific. So what would you write out? And what would you do to find or get the y by itself to determine your inverse? Okay, so I'd have x squared is equal to y inverse, or my inverse function, even though it doesn't use function notation, I'll use it, is equal to x squared. But that should not sit well with some of you. If you are actually thinking and engaging, think about that for a minute. Mentally engage and envision the graph. Something about this shouldn't make sense. What? You're saying this should be negative x squared? No? No? Because we didn't take a square root. You squared something. If you took the square root, it would be plus or minus what? No. It has to do with our inputs. If I graph out y equals x squared, what shape is that going to be? What shape is y equals x squared? A parabola. So I'm going to sketch that out and not on yours. I'll do it. So I'm here. I graph out a parabola. It's going to look something like this. Remember, the inverse is the reflection over the line y equals x. What's the problem with the parabola? We need to restrict down the domain on it. Because right now, am I giving too much or too little? Too much. What part of this do I not want to see? Hands up, please, if you can tell me, what part of this do I not want to see if I'm looking to go through and take the inverse? We want to see the right. We don't want this garbage over on the left. But we only need to see half of it. So what can we do to say, all right, it's that equation, but not that? What do I do to make that happen? What? And we'll state after it that it's from 0 to positive infinity. Because when you gave the square root, when you're taking the square root function, that's half of a parabola. It's plus or minus, it would be a sideways parabola. But you have to be at that point. You have to, and we were talking about it with the other section today. I sit here, how many times last year were the equations that you worked with, did they look like this? How many times did that happen? Is that pretty much every day? Was that as tough as they got? Yes or no? They were tougher? Did you do quadratics? A lot of them? Every day? All day? Please. That's what you need to be doing. Every single day. No offense, I could go through, you learned how to solve that in 7th grade. Equations like that have no place in a high school. Now, we got through our inverse, we restricted down the domain. I'm going to get rid of this and this. That would be the inverse of it. We didn't do odd, even, or neither yet. Is the function 1 to 1? So look at the original function. And with that, Jared, is that going to be 1 to 1? Who agrees? Who disagrees? Who can tell me why they disagree? All of a sudden you lose opinion. There you go. In order for it to be 1 to 1, this answer here is going to be yes. Is it 1 to 1? Because it passes your vertical line test and your horizontal line test. What about an onto function? Does anybody remember what an onto function is? 1, 2 of us. We did it. This is the 3rd time we've referenced it now. They don't go away. What do you want to say? No. If it's 1 to 1, the inverse will be a function. What do you know about an onto function? It's when all the y values are used. Look at that graph. Does it use all of the y values? No. If you don't know it, make sure you start knowing it. Any negative y value is not used. Questions on that? There's no asymptotes. This we're saving for trig, so we got one more question to answer. As x goes to positive infinity, what are the function values going to? Hands up, please, if you can answer that. Look at the graph. As we go out to positive infinity, where are the function values going? One person, 2, 3, 4, 5. Positive infinity. By the way, somebody, I can't recall who, somebody today came to me and asked a question about the Math Excel. When you input on the computer doesn't need you to put the positive in when you give infinity, but when you handwrite it out, I ask that you do. As x goes to negative infinity, what are the function values going to? Now, let that process what the question's asking. As x goes to negative infinity, what are the function values going to? We got 2 people who can answer that. Okay. Yeah. Does x go out to negative infinity? Where does it hit the wall at? 0. So we're going to say that this does not exist. Because the function's not happening over there. It hits 0 and we're done. Now, set that aside. Put it with function of the week number 1. At the end of the year, hopefully, these should be getting much quicker. Should be. And hopefully next week we'll know what an onto function is. Now, have your homeworks out. Before we do it, just so you're aware, here's what the answers to your assessment should be. These are people from the first class. When we say show out your work, this is exactly what we're talking about. If you don't know your square roots by now, and you're in an honors class, you've got to make sure that you do, because it's not cute anymore. And again, it's just you guys, it seems like they sort of push you through like cattle going into McDonald's hamburger factory. They just, no matter how good or bad you are, they just load you right into the chute and they go, okay, you existed for another year, here you go. You've got to know what your square roots are. Square root of 64 is 8. And then when we take the square root of x to the, or a to the 6, we get a to the 3rd. Same thing. There were some that were difficult, but again, square root of 36, we can't be getting that wrong. X to the 7th, you can take the square root of the x to the 6th and leave an x underneath, and you can take the square root of y squared. But we should be able to get these. Cube root of negative 8. What's the cube root of negative 8 going to be? No. Negative 2. Cube root of 24, well, 24 isn't a perfect cube, but what is? 8. So you've got to be able to go through and do those out. Those are what the answers to that are. They're worth 2 points apiece. 1 if you got your foot in the door, 2 if you got the whole thing right. The other thing is, here are the answers to the homework itself. So go through right now. If you've got any questions, make sure your name is at the top. Go through and check. How did you do on the actual homework? Take a look on your papers at 61. So I got a message regarding this the other day, and it was a perfectly valid question. If you go through and you look at 61, that's this one here, you go, I don't know what to do. We'll say this, do what you can do, because again, we're giving you very, very complicated questions. Do what you can do. So you're going, there's not a double square root there. We didn't do anything like that, and they're absolutely right. If you wait for us to go through and cover every possible math question that you're going to exist, it's going to be a very long year. Do what you can do. I look at that and I go, all right, well, that's a square root of, look at what's in the red. I don't know how to do a double square root, but I don't need to. Look at what's in the red. That was the original. Can I take the square root of the inside stuff, which is 16x to the 4th y to the 4th? Yeah. And that leaves me with 4x squared y squared. And that's still in the radicand position. After simplifying it out of the first one, now from there I can go through and get 2xy. I'm not going to be able to give you every question. It's getting that first effort in. Show me that you're fair doing it. There were people that we had in the last section who screwed up this piece here. They go, I don't know where this came from. Simplify out. It's the cube root of, what's the square root of what's inside for 62? Hands up, please, if you can tell me. What's the square root of what's on the inside in 62? We seriously have 5 people that can tell me. 6? What do you want to say? 8x cubed. Good. 8x cubed y to the 6th. But now I need to go through and take a cube root, but I'm loving this question. Because after taking a square root, what can we do to go forward with this? Cube root it. And what do we know about all the values that are there? They're perfect cubes. What's the cube root of 8? That's where that came from. Any questions that we need to see? Those are all your answers. All right. Make sure, please, that your name is at the top with a -3 after it. And let's have you hand those up and over now, please, as well. And have your notes out and open. Let's go. Hand them up and over. Have your notes out and open to page 6, I believe. Is that where we left off last time? Yes or no? Page 6? All right. Hand those up and over. Let's go. We left off here. Now, we left off on the bottom questions for page 6. What you need to know, if you're adding and subtracting radicals, they need to be alike. So you have to have like radicals or indexes, plural of that is indices, and like radicands, which means the value underneath there needs to be the same. In order to add or subtract, you need to have like radicands and indices. Now, here's our first one up. First thing I ask myself is, it's root 27 minus 3 roots of 12. First thing I need to ask myself is, what are my perfect square numbers? Because that's a square root. So, and this happened in the first class, and it struck me because it just indicates sort of a, I don't want to say, it seemed very weak intellectually. I go to the group, who can tell me what these perfect squares are? Somebody started listing them off like that, and they're like, 4, 9, 6, 6, and they kept going. And they kept going. And they turned around and they go, they're like a calculator. They're not like a calculator. They're paying attention. You're in an advanced class. Some of you, how old are you guys? 15? Is that right? So you're 1 year away from being able to operate a 2,000-pound vehicle at 60 miles an hour legally. And we're freaking out and can't do 2 times 2 or 3 times 3. And then it gets really difficult because, of course, we'd freak out if I asked you to do 7 times 7 in your head, or maybe rapidly do 8 times 8 or 9 times. We have to be able to get that. Our perfect squares. 4, 9, 16, 25, 36, that's 6 of 49, 64, 81, 100, 121, and so on. What perfect square goes exactly into 27? Hands up, please, if you can tell me that. We'll wait for 6 of us. I've got 1, 2. I need the biggest perfect square that goes exactly in. 9 times what?
9 times 3.
There you go. So I'm going to break this down, and in the beginning it's okay to write it out like this. 9 times 3 minus 3. I'm not going to list out radical 12. How can I break down radical 12? Now we're going to start going through and taking some square roots. So looking at this, I've got the square root of 9, that's 3. Square root of 4 is 2. Now here's the part, all of you should be on solid ground listing out 3 roots of 3 to start. Who can tell me what that second radical is going to be when I reduce down our radicand? We got 1, 2 of you. Take that step. What do you think it's going to be?
6, 3.
Because you're multiplying those values. It's 3 times root 12. So now it's 3 times 2 times root 3. Do I have like radicals, meaning that the index and the radicands match? Sure. So now let's go through and subtract our coefficients. Negative 3, root 3. Next one up. Now we're going to start working with cube roots. So before we start freaking out and yelling, they're a calculator. Who can tell me, please, what our perfect cubes are? So I'm going to make a list of them in the margin. Not all at once. What do you want to say? 1, we're not going to count 1. What's next? 8, then what? Then what? Then? So that's 1 cubed, we don't count. 2 cubed, 3 cubed, 4 cubed, 5 cubed. Does anybody know what 6 cubed is going to be? 6 times 6 is 36, times 6 again. See, the part that's scary, go to your calculator if you need it. I don't care. I'd rather you get it right than you sit and stare at me like my face is a calculator. Let's ask this. How do I want to break down? By the way, we all have cube roots in number 2. but they're not like radicands. That's why we can't just go through and add or subtract them. What would I do to simplify this down? Talia, what would you do to start off? Okay, so that's the first part. And by the way, some people might be thinking, well, that's the square root of 16. If it was a square root, you'd be absolutely right. It's a cube root. Robbie, what would you go through and how would you break down the second piece?
It'd be 2 cube roots, and then 5 times 5 times 2.
No? Close. What's the, what number goes here? Because it needs to be equal to 250. You're taking the square root or cube root. Don't take that yet. Who can tell me the number that's supposed to go here? The 125 goes here. When we simplify, we'll pull out the 5. Now, the next piece is minus 3 cube roots of 2. Do any perfect cubes go into 2? No. From here, I'm simplifying this down. Cube root of 8 is 2. Cube root of 125 is 5. So how would I rewrite this out now? Leah? What's that? No, not 20. What's 5 times 2? 10. And then the cube root of? Keep going. I now have like radicals. So, Amanda, what am I left with? No? Go across. And then 10 more is? $17 cube roots of 2. Some of you are very good and don't need to show that much to get that done. And that's fine. You could, when you're good, you'll go from this line here down to this line, and that's completely acceptable. Let's keep going. Now, if A and B are real numbers, we know that we can break this down. We can take a product, and it can either be housed under the same radical or separate radicals. And the same thing happens with the quotient. If the indices are the same, I can go through and either break it up or put it together. If it's a product, I can break it up into 2 fractions or put it together under 1 with with that index if it's a quotient. Now, taking a look at what we have, let's make sure that this gets down. You dealt with this the other day, whether you would remember it or not. We had a question where it was the square root of x over 2, and we broke it up into root x over root 2. And that's what you've got to be able to do. Sometimes you want them together, sometimes you want them apart. You want to look for a reduction, you put them together. If you're trying to simplify, sometimes you want to break it apart. Questions on this? Let's look at our first one here for number 3. If you had to go through and do number 3, we're going to multiply our coefficients, then our radicands, and get an answer. So, Hannah D, what would you get if you multiplied the coefficients together? And then what's your radicand going to be when you multiply going across? Now I need to simplify down the radical. You're lucky that it's an x squared and y squared. How do I want to break down the 12? Noah, what would you need to do?
4 times 3.
What can I take the square root of, Maddie, that's currently there? Which is? What else? Which is? And? Which is? So what's your final answer going to be? Questions on that? Now we're going to do a perfect cube. So get down what number 4 is. We're going to have to multiply across to get what our answer is. So when I multiply across, Ben, what is my coefficient? What will my coefficient be? Negative what? Negative 2. What's under the cube root now? No. Multiply your radicands. Here's what you're multiplying together. This and this. Multiply them together. What do you have? I'm actually kind of relieved to see 30 there. Why is 30 not bad to see right now? Why is this easy? Can't be simplified down. So looking at what's there, I'd say, all right, we've got negative 2, that cube root, etc. There is one part, though, that I do need to break down. Which piece of this do I need to break down in order to go forward? 2, 3 of you. Okay. What's the y going to be? No. You're taking the cube root of y to the third. Just a y. I want to break this up too. How would you break down the x? Or what would you be left with? No? How many times does 3 go into... So, what's going to be left and where? There'd be an x left underneath, and what's out front? How many times does 3 go into 7? So it'll be x squared. Now in front, what would you leave, Nathan, as your final answer?
It'll be negative 2x squared y times cube root of 30x.
I look now at number 5, and there's work that we can do in number 5. Looking at what's there for number 5, I see that and I go, that can break down, and it's kind of easy to break it down. The first thing that you've got to recognize is there's 2 radicals. Let's house everything under 1 square root and see if we can break it down. So this would be the square root of 56, x to the 5th, y to the 5th, all over 7xy. Abby, what is that going to simplify to? Well, just do the division. What's 56 over 7? Eight. Now simplify the x's and the y's. So what's left with the x's? Y to b. Now, we're going to simplify from there. Jessica, what can you simplify out that's currently there? So that we can simplify it out too without saying I'm okay with this. So what would you give out as your final answer at this point? Because everything, in all honesty, if you can't do this part in your head, you're not as far along as we need to have you. So what's the square root of 8? What will that break down to? 2 radical 2 on the inside. What about the x's and the y's? You can go right into that. go forward. Let's try out number 7. Looking at what's there for number 7, I look at this, there's all of this division going on. I want to simplify things down. So Taylor, what would you go through and do? What could you do, I guess, to reduce this? 15 divided by 3 is going to give you how much? Okay, that takes care of the outside. Now, she's talking about take 60, x to the 5th, y all over 12, xy cubed. Now, can you simplify down what the radicand would be?
Yeah, it's going to be 50 x,
It would be what?
or 5, sorry.
Yep.
5 x to the 4th. Y.
Which side has more y's, the numerator or denominator? By how many? No, 2. Now, there's parts of this that do simplify down and simplify down nicely. Who can tell me something that's up there right now that we can work with to go forward? Christina, what do you want to do? What's the square root of y squared going to give you? And what's the square root of x to the 4th going to give you? Now, the way I wrote this technically is wrong, but let's see if we can make it right going across. What would I have out front, in front of the radical? What expression is going to be out front, in front of this radical? 2 of us? 3, 4. Look at what's there. Follow it forward. What would you go through and have? John Paul, what do you say? And then what's left in the radicand? Careful. 5. What he did so correctly there was you recognized that when you take the square root of it, what you're actually taking the square root of is 1 over y squared, or what times itself gives you 1 over y squared, and that's 1 over y. That's because y is not in the bottom of a fraction, but in the denominator of a fraction. So that's what we would get. Questions on that one? We're going through the 4th. Same process for the 4th. Now this is the part, we're going to have to go through this quickly. Some of you do this fun box of multiplication or whatever it is. It does you no favors. When we do this out, we'll list it out as first outer, inner, and last. You're taking a double distribution. You're taking a product 4 times, combining like terms. When we do this, we're going to multiply our first terms together. So looking at what's there, Alex, what do you get when you multiply the first terms together? No.
Oh, 6.
6. Now I'm going to take and multiply the outside terms together. So, Nick, what would you get when you multiply the outside terms together?
3 rational 5.
Close. Negative. What about the inside terms, Erica? Now, we're going to take a little bit of a mental math jump here. Captain, what do you get when you multiply the last terms together? Negative 5, because you recognize root 5 times root 5 will be a negative root 25, which you can simplify down. Let's put our like terms together. And Anna, what would you give out as your final answer? You got like terms here, here, and then these 2 in the middle. So put the outside ones for your constants first. What's 6 minus 5 going to give you? 1. And then what do you get when you put these together? No. Negative 3 root 5 and positive 2 root 5 is negative 1 root 5, or just negative root 5. Questions on that one? Now we're going to do one that's a little bit more interesting. Looking at what we have here, let's FOIL this again. First outer, inner, last. Jaron, what do you get when you multiply the outside terms?
5 times square root of 3.
No, sorry, first terms, I'm sorry. First terms. Good. Now let's do the outside terms.
5 times square root of 3.
Inside terms
Negative 5 times
and last terms.
negative 3.
What's nice about what we just had happen? Hands up, please, and tell me. What's good about this? This is easier than the ones that you just did. What's nice about what just happened?
This positive fraction.
Nothing cancels, they always reduce. We don't say cancel in here. Let's ask this very simply. If you have 7 over 7, what does that become? If something cancels, is it there anymore? No. 7 over 7 reduces to a number value. What number value is it? 1. Therefore, there's no such thing as canceling. Things reduce. Now, looking at what's there, what do we get when we combine like terms? Look at those two binomials that you have. That happened. The outside and inside reduced by design. They're supposed to go away. They're supposed to simplify out. If you've got an outside and inside, how do those, well, let's ask this. If that happened by design, what do you notice about those two binomials? Look at what's there. Use your eyes. Look at the two binomials there. What do you notice about them? What? Close. I don't want to say opposite because then you'd have to fully negate one of them. But what do you notice about the sign in the middle? That's an opposite. So what we have is called a conjugate. And I don't know if this is on your papers or not. But the conjugates are two binomials that differ by the sign in between them. If I take a plus b times a minus b, that's going to become a squared minus b squared. There's no middle term. Now, we're going to use that to help us out. We're going to bounce forward to a question because we're going to use it anyway. Take a look, please, at question number 13. Looking at question number 13, I can't leave something like that as a final answer. Hands up, please, if you can tell me why. Why is that expression never permitted in Algebra 2? John Paul, what do you say? I need that radical to go away, which means I'm going to multiply by the conjugate of the denominator. So that's going to be 2 minus root 3 over 2 minus root 3. Now the numerator should be really easy to handle and to multiply. By the way, I multiplied this by an ugly 1. That's what we'll reference this. I jumped ahead for a second. We're multiplying by an ugly 1. If you multiply something by 1, does it change its value? No. So now, what am I going to get in the numerator? Eli, what would you have if you distributed the 5 out in the numerator? Close. Distributed halfway. 10 minus what? No. 5 times root 3. Now, down below, we've got a binomial that we need to square. So do that down on a little bit of a separate area here because we don't want it muddying up the question. We've got 2 plus 3 times 2 minus root 3. If I FOIL this out, my first terms would give me a 4. The outside terms give me a negative 2 root 3. The inside terms give me a positive 2 root 3. And my last terms are going to multiply together to give me a negative 3. What happened? What's the benefit of what we just did? Those are now gone. What's 4 minus 3 going to give you? 1. So your final answer would be 10 minus 5 radical 3. To get that out of there, you need to multiply by the conjugate. The only thing that changes is the sign in the middle. Let's do one more. I've got a radical in the denominator. I'm going to need to multiply by a conjugate. My conjugate would be 1 plus root 5 over 1 plus root 5. When we do that out, in the numerator, you need to FOIL that. First, outer, inner, and last. So that means first terms multiplied together, we'll do in the margin, you've got 1 plus root 5 and 1 minus root 5. So this would be 1. Outside and inside are going to reduce, minus 5. Oh, sorry. That would be for down below. So this gives me a -4, and then in the numerator, I would go through and take that product. You've got 1 plus root 5 times 1 plus root 5. That's going to give you 2, it's going to give us 1 plus 2 root 5 plus 5 at the end, which would be 6 plus 2 roots of 5. What do all of those have in common? What is there? 2. So let's divide it out. Your final answer would be 3 plus root 5 all over -2, or you could bring the negative up front if you wanted. Those answers mean the same thing. Your homework is done on separate paper tonight. It's out of the packet again. Questions on that? All right, then make sure, please, that we go through and get this done. When you put your calculators back, make sure they go in the right spot. Yes, I can stay after while coaching is going on. I will stay